Well, good morning. Uh, First, I apologize for the late. Uh, First, an announcement. I actually posted the next assignment, the assignment for chapter 4 and chapter 5 on the blackboard. So we haven't started chapter 5 yet, but chapter 5 is relatively small topics. Um, it's not because the topic itself is small, but it's just because I want to make it small. Um, Chapter 4 is about concurrency. You know, when multiple actually processes actually are running, they try to access the resources, and these resources are shared among them. So you have to actually coordinate. Um, you have to coordinate among all these processes. Chapter 5 is about deadlock. Uh, Deadlock is actually a big topic, but I decided to minimize it because in many cases, many operating systems actually choose to ignore the deadlock. It's not because deadlock does not exist. It's because sometimes um, if you have a multiple processes just fighting for the resources, and there's a kind of scenario that many actual processes they try to actually finish their job. They need a resources to complete the job, but uh, but because limited resources, they can't. They have to wait until other process complete the job and then release the resources. When I say resources, these are I mean the hardware, the CPU, the memory, the printer, scanner, and all these hardware resources. These resources are shared among the processes. Now, when a process actually waiting for resource to complete the work, sometimes they cannot get the resources, so they have to wait. And this is actually this is not good because if a process actually is started and the process wants to do its job, but they need the resources. They need to acquire some resources to complete the job. But if a resource is not available, the process has to wait. You know. Now, if a process is waiting for a long time, um, it's going to cause some kind of a scenario called starvation. You know, so starvation is not really good because one of the example is um, in 1960s, one of the computer systems in Stanford, they have been up for running for like a couple of years, and then the computer scientists they try to clean up the computer systems, and they find out there are some processes they have been they have been created for more than a year, but never going to be able to complete. You know, so these actually processes actually they're not going to be able to finish, but they're taking the resource by themselves because they are up, so they're taking the memory space, they're taking the you know the sometimes the CPU time, but they cannot complete the job. So so starvation is a kind of issue. So we have to resolve. And deadlock is it's kind of things that it happens when some process is actually waiting for resources to complete the job, and the other process is also waiting for resource to complete job. And deadlock is actually kind of situation that you know one process one, is holding some of the resources, but still cannot continue the job because the process one is still waiting for some other resources. Now, while the process two is holding some of the resources, and waiting for the resources that is currently held by process one. So, and the process one is waiting for the resources currently held by process two. So each of these two processes actually held the processes other held the resources that the other process is waiting for. So that's a kind of situation. That's a deadlock. So if process one is not give up the resources it is currently holding, then process B never going to be able to grab these resources and complete job. And the same situation happens for the process two. If the process two, if process two, you know, doesn't actually release the resources that it is holding, process one cannot complete the job. So they hold each other's resources and they're waiting for the resources that the other one is holding. So that's kind of deadlock situation. Um, Sometimes deadlock actually happens. That's the truth. And so that's why people try to figure out a way to either prevent deadlock, make sure deadlock never happens, or resolve the deadlock. If the deadlock actually happens, how can I resolve this? You know, so it's just like some kind of a situation when two vehicles, so they drive on the opposite direction, and then it happens to be that they both try to cross the bridge, but the bridge is narrower than the road. So bridge has only one lane. So the road is two lane, but the bridge is one lane. So they actually both try to cross the bridge, try to drive across the bridge, and then they're deadlocked at the bridge. So in that case, how to resolve this issue? One of the vehicle may need to back up and make a room for the other vehicle to pass, right? That's one solution. So, but you need actually a police or somehow you need some kind of a mechanism to prevent, to number one, prevent deadlock to be happening, or number two, try to resolve the deadlock situation. And there's a third solution. That solution is to ignore the deadlock, pretend the deadlock never exists. Um, but the truth is deadlock is there. So what happens is that when people actually, you know, run the computer system for a long time, the system performance is actually going down. They know actually sometimes the deadlock happens. Some of the processes is holding some resources, but never going to be able to finish. Now, one easy approach is to turn off the computer system, you know, clean up everything and then reboot the computer system. So that's one solution. Okay. So that's chapter 5. So we're not going to spend much time on chapter 5, but first let's finish the chapter 4 topics. Okay. So last time we talked about the produce and consumer problem. Produce and consumer problem is a typical problem where two processes actually coordinate to each other. You know, so so in this producer consumer problem, there are two processes. Process one is called producer. Process two is called consumer. Okay. Now we mentioned that um, process producer and consumer they're actually working collaborate you know collaboratively to you know to do some kind of business. you know one you know they have shared data. Okay. um it's the buffer that the shared by both producer and consumer. you know the buffer can be interpreted as a warehouse. So you think about like Walmart or Costco, when they try to manage all these consumer stuff, so they need a warehouse. So the producer going to produce the product, and once they complete the product, they put in the warehouse. Okay, so and if the warehouse is full, the producer, they can continue to produce the stuff, but they have to actually wait until the warehouse is empty so they can put more product into the warehouse. So if the warehouse is full, the producer cannot put more products into the warehouse. However, the consumer need to actually consume the product, ship the product out of the warehouse and sell the product to the customer. So this warehouse is kind of like a shared data. Okay. So in computer, we use buffer to simulate the warehouse. It's all we call shared storage. So the producer has four actual steps. One is step one, producer produces the data item. Okay. So you can interpret this as, the producer actually make the product. Okay. And then the producer place the data into the buffer. Once the actual data is actually produced, this is actually a time period that producer produced the data into the buffer. And then once they put the data into the buffer, and they mark the buffer as full, they raise the flag, say, okay, the warehouse is full. Okay. And then the producer can then continue to produce next data item. Okay. However, since the buffer is full, the producer can produce the next data item, but they have to wait until the buffer is empty. So these are the four steps. Okay. And the consumer also requires a couple of steps. The consumer basically wait for buffer full. Okay. So the consumer need to make sure the warehouse has products in there. So once the actually consumer find out, oh, there's a flag over here, the flag says, okay, it's full. And the consumer then remove the data from the buffer. And that's one of the process, that to remove the data from the buffer.
Professor?
Yes?
Can the buffer only hold one data item at a time, or can it hold like variable amounts of data?
At this moment, we're talking about the buffer only hold one data item. Yeah, you bring up another question. That's, so when we talk about a buffer which can hold multiple items, right? Now that's kind of different. But at this moment, yes, we only talk about a buffer which we assume that the buffer can only hold one data item. So we want to simplify the version first. So then the buffer, once the buffer is full, once the consumer actually remove the data from the buffer, and the consumer going to mark the buffer as empty. So in that case, you can interpret like a consumer just actually put down the flag, says, okay, I remove that item. And then the producer actually keep watching while the computer producer is waiting, watching the flag, and the flag is down. So say, oh, the buffer is empty. So then it's just that the producer going to repeat the process. Now we mentioned that in these couple of different steps, two steps are important. That's this step: place data into the buffer, and then mark a buffer as empty, as full. So these two steps are very important, very critical. And we call these two steps the critical section, because these two steps are the steps that are gonna actually access the buffer, change the actual status of a buffer. So that's why we call it critical section. Okay. Now produce the item, wait for buffer to empty. These are basically instructions that does not impact the buffer, but only these two going to impact the buffer. Okay. Now for the consumer side, remove data from buffer and mark the buffer as empty. These two steps are also defined as critical section for the actual consumer, because these two steps can actually change the status of the buffer. So the buffer is shared, and the critical section is a fragment of the code that they're going to actually access the shared data. So that's why it's defined as a critical section. Now the general rule of thumb is, if one process 1 or process 2, if one process is in its critical section, the other process cannot be in the critical section, because you cannot actually allow both process to access the buffer, and one process is putting the product into the buffer, the other process in the meantime remove the data from the buffer. This is going to cause some confusion. We're going to find out why. Okay, so that's the producer and consumer problem. Okay, now let's take a look at the example. This is in the Zybook. In the Zybooks, it's exercise 4.1.1. It's a possible code interleaving. Okay, we try to check out the case of how the two process actually just running concurrently, they actually somehow collide each other. Okay, now let's take a look at this first. Let me show you what it. Okay, it's a exercise 4.1.1. That's okay. Let me move this over here. So that's the exercise 4.1.1. Possible code interleaves. A process executes a sequence of a machine level instruction S1 to S3. Another process executes its sequence R1 and R2, determine all possible interleaving of the instructions when processes are run concurrently. Okay, so that's this. So let's see. Try to write something on there. Okay, so here's a process 1. So process 1 going to execute the sequence of a machine level instruction S1, okay, S2, S3, okay, and another process execute the sequence of R1 and R2. So it might be like a process 1 execute its instruction, and then at a certain point the process 1 going to execute the machine level instruction S1, and then later on S2, and then later on S3, and we can then continue, and the process 2 going to do similar things. Okay. Now, basically, we want to talk about so determine all possible interleavings of the instructions when the process runs concurrently. So these two processes are running concurrently. So what are possible scenarios? Why we want to talk about this? Because it's so important. Because if we use some kind of multi-programming, mechanism like using round robin, so if both process 1 and process 2, they are running concurrently, but they share one CPU. If that's the case, then round robin is the option. So the process 1 may take the CPU and execute, and then switch to process 2, and process 2 gonna actually running in the CPU, and then switch back to process 1 and switch back to process 2. So round robin gonna, if the scheduling algorithm is used, then the CPU gonna switch back and forth between P1 and P2. Now this gonna cause some kind of scenario that it might be that the CPU is actually running S1, and then next one CPU is then gonna run S2 and then run S3, and then R1, R2, or it's kind of like a CPU gonna run S1, then switch to process 2 and run R2, R1, and switch back. So that's the scenario that because if they are running on different CPU, they are running concurrently. You still have some kind of scenario that if this is a time, okay, this is a time, okay. Now you might have a scenario that okay, P1 is running, and the P1 at the particular time, P1 actually start to run execute the instruction S1, and then at the next time it execute R1, and then S2, and then S3, and then R2, right? So that's the some kind of interleaving. That's one possibility. But how many different possibilities? Now in this case, if they switch back and forth, that means the CPU gonna run this S1, then switch to SP2, and then run R2 is actually R1 is actually next instruction that the CPU gonna execute, and then switch back, and then continue to run IS3 and switch to R3. So CPU gonna switch back and forth. But there are many different ways the CPU gonna execute these these instructions. Okay. Now determine all possible interleavings of the instructions when the process runs concurrently. How many different possible case? Let's see. Let me just erase that. Can you figure out how many different scenarios? It could be S1, S2, S3, and then R1, R2, right? So all the instructions in P1 basically executed before the instructions in P2, right? Now what matters is you have to make sure S1, S2, S3, they should be running in this actual order. And R1 and R2 running in this order. But there's no guarantee that S1 should be running before R1, or S2 should be running before R1, or S2 should be before R2, right? There's no such a, because they're running in parallel. They're running concurrently. So it could be like, S1, S2, S3, they are running. Or could be another scenario. S1 S2, and R1, S3, R2, right? Or could be S1, S2, R1, R2, S3. Now, all I need to care about is that the S1, S3, S2, S3 should be in this order, but not necessarily with R1, R2. So R1, R2. R1, R2 should be, you cannot have R2 before R1, but that's not possible because R1 and R2 are two instructions that are running by, are executed by one process. So in this case, if it's executed by one process, if R1 is ahead before R2, then that's always the order. Now S1, S2, S3 are basically under the same situation. S1 has to be before S2, and S2 has to be before S3, because it's in the same process. But you never know, S1, R1, because these are two processes. Okay. And S1, R1, S2, S3, R2, S1, R1, S2, R2, S3, or S1, S1, R1, R2, S2, S3. Okay. There's so many different scenarios, right? And the last scenario could be R1, R2, S1, S2, S3. Completely, the second process, all the instruction in second process is going to be executed before the process in the instructions in the first actual process. How many different scenarios? So it just requires a math, you try to actually include all these different combinations of S1, S2, S3, and R1, R2, R1, R2. So, okay. So I'm not going to be able, I'm not going to actually list all the possible scenarios, but you can, right? So you can just arrange these S and R instructions. So in all the possible ways. Okay. Now here's another example. This is a very interesting example. Okay. So this gave you the idea why why it's so important to set up the critical section. Okay. Now, here's the example. The following program is executed by two processes, P and Q, concurrently. Okay. So here's a P. Here's a Q. Now, at a certain position, P gonna run this for loop. I equals 1, I less than or equal to 3, I plus plus. So which basically means this x equals x plus 1 will be executed three times, right? So I'm going to say x equals x plus 1 will be executed. And then after you finish the first loop, it will be executed again. And then it will be executed again. Okay. Same thing with Q, right? Now, this x is actually used by both sides. So that means you can interpret x as a shared variable. So both P gonna update the value of X. Let's say the initial value for X is 0, okay? Initial value is 0, okay? Now, after P execute the X equals X plus 1, then the value of X gonna be updated to 1 because initial value is 0, 0 plus 1 and assigned to X. So X can be updated to 1. And I execute again, then updated to 2, execute again, updated to 3. Now, same thing with Q. Q is also going to update the X, okay? Now, if we think about the previous exercises, okay? So let's say if these actually two processes running concurrently, there's a scenario that you're going to be executed X equals X plus 1, then execute this one, and then execute this statement. And then execute this statement, execute this statement, execute this statement. Or you can execute this statement and switch to the other side and execute this statement and switch back, execute this statement. So you can say 1, 2, 3, 4, 5, 6. So you can have a 1, 2, 3, 4, 5, 6, or 1, 3. Oh, that's 4. So 1, 4, 2, 5, 3, 6, or 1, 2, 4, 5, 6, 3. So you may have a various different combination. Okay. However, since these 6 statements are basically perform the same operation, it really doesn't matter whether we mix or not, right? So if the initial value of X is 0, what do you expect after actually P completed all its operation, all its statement? What is the value of X? P gonna increment once, increment twice, increment 3 times. So what is the value after this? If the initial value of X is 0.
If P and Q are running concurrently, it would be 6, right?
Eventually, you expect that this is going to be a 6, right? Yes, it should be 6, right? It doesn't matter in which order, right? If you think about all the possible interleaving. But since all these 3 operations basically perform the same thing, just increment X. So really, it really doesn't matter. However, if you study further, if you know how these computer system actually works, then you will find out there's some problem with this approach, this kind of approach. Okay. So typically, when you write X equals X plus 1, that's you basically increment the value of X. So X is actually stored in the memory, and then you increment the value of X, and X becomes 1. If initial value of X is 0, right? And then you increment X, X becomes 2. So sounds very straightforward. However, if you look at the computer system and how the computer system actually works, now this operation X equals X plus 1 actually consists of 3 instructions. Okay, consists of 3 instructions. One instruction is so it's basically, so it requires that the load the value of X from the computer memory into a register. So there's X equals X plus 1 requires 3 extra instructions. The first instruction is load X. So that means here's the computer CPU. Here's the memory. Now here's the value of X a variable stored in the memory. So here's the register. Okay, so you're going to load X into the register. Okay, load X into the register. And then the next step into register, I say register 1, whatever the register, it doesn't matter which register. And then the incremental register. So register 1, and if X initial value of X is 0, and 0 going to be loaded into the register. And then you're going to increment the register. So the value of register becomes 1. And then you actually save the value in the register back to X. Okay. Okay. So you have 3 steps. Okay. So these actually, each step are actually going to be an instruction. So you basically consist of 3 instructions. Now, let's actually take a look at the details of this. Let's say I'm going to say, first this instruction says, oh, I don't know why, just disable the writing mode. Maybe. Okay. So you can actually do this, saying, here's the, a register. Okay. I need a register. I call the register 1. The register is actually in the computer CPU. Okay. So when process 1, when process P, I'm sorry, not 1, that's P and a Q. When process 1 execute this, so the process 1 need to load, fetch the value of X, and load it into register 1. So then register 1 should get the value of X. That's the first instruction. So in this case, and then you increment the register 1. Register 1 equals register 1 plus 1. And then you basically assign the value of register 1 back to X. That's the 3 instruction, And again, you need a 3 instruction. Okay. So in this case, you're going to say register 1 equals X, register 1 equals register 1 plus 1, X equals register 1. And the same thing. Okay. So now, similarly, for the Q, you might actually need the register 2, right? Another register, because it's independent operation. So when Q is executing, so then the value of X is going to be stored in the register 2. And then register 2, I put the plus plus increment itself. And then register 2, the value of register 2 assigned back to X. Also 3 steps. Okay. Now, if that's the case, now think about this. Okay. So when P start to execute, and P actually execute the first instruction here. Let's see. Now, register 1 equals X. That means assign the value of X into register 1, right? Then I have a 3. So initial value of X, and register 1 equals X. So then the register 1 will get 0 because the value of X can be copied to register 1. And then the register 1 increment by itself, the value in the register 1 becomes 1. Now, before you actually save the value of register 1 into X. The value of X is still 0, right? So the value of X over here is still 0. And then when you actually save the value into the X, then X becomes 1. The register is still 1, right? So now the value becomes 1. X of X value becomes 1. That's the X. That X is in the memory, and registers are in the CPU. Okay. Now, if I actually execute the next one, so next one gonna be executed by Q. So then X assigned to register 2. So because the value of X is 1, so then the register 2 will be 1, right? If I run this. And then incremental register 2. Register 2 actually equals register 2 plus 1, so it becomes 2. Now in this case, X value is still 1, and here is still 1, until when I actually say X equals register 2, and value of register 2 assigned to X, then X becomes 2. So value of X is incremented. Now everything looks fine at this moment. Okay. Now what about this? The computer actually, CPU switch to P and execute this instruction now. So X assigned to register 1. Now the value of X is 2, right? When X assigned to register 1 and register 1 becomes 2. Okay. Now I increment the register 2. Okay. On register 1. So register 1 becomes 3. Okay. But the value of X is still 2. Now at this moment, the computer CPU scheduler say, I want to switch to process Q. So the process Q gonna actually start to execute. Okay. Now the process 2, the process Q actually execute the first instruction of the second increment. So this first instruction gonna assign value X to register 2. So what is the value of X in register 2 in this case? Oh, what's the value of X? It's still 2, right? And then I increment the register 2. Okay. So I increment the register 2. Becomes 3. And then I actually, register 2 equals X. So I copy the value of register 3. Copy of register 2 into X, which is 3. So X becomes 3. And then after finish this, the CPU scheduler say, well, I want to switch back. Okay. So P1 gonna continue this instruction. This instruction say register 1 equals X. Or X equals register 1. Now what's the value in the register 1? Also 3. So 3 gonna be copied to X. Okay. Now here in this diagram, I think I mess things up because I just actually say switch back and forth, but I should actually really draw the timeline. Okay. Let me actually just clean up this mess and just clearly just give us an idea what this is really is. Let me actually clean up this mess. Okay, let's see. So here's P, and here's Q. And instead of I writing x plus x equals x plus 1, I just say, okay, register 1 equals x, and the register 1 plus plus increment, and the x equals register 1. So this basically is 3 actual instructions that represent this operation. Okay, so that's the x plus 1 operation. X equals x plus 1. And then, now, we basically assume that after actually P completed all its operation x equals x plus 1, and Q complete all its operations x plus x1, and the final value of x is 6, right? Initial value of x is 0. And then we believe the final value of x should be 6. Now, this is based on the assumption that x equals x plus 1 is just one operation, one piece of operation. So that means if once P actually executed register 1 equals x, and then this 3 actually instructions should be completed as an entire operations. It's not separable. Now, however, things might be different. If I say, okay, now register 1 equals x, so here's the register 1, and here's the register 2 used by Q. And then x initial value of x is 0. So when I say x register 1 equals x, so x, the value of x is going to copy to register 1. So register 1 gets 0. Okay. And then you increment the register 1. So register 1 plus 1 assigned to register 1. So register 1 becomes 1. And then register 1 assigned back to x. So the value of x becomes 1, right? Now I think about this at a time. And then if it's nicely actually organized, then you're going to say register 2 equals x, and register 2 plus plus, and the x equals register 2. So that means if I actually switch to process Q, the process Q going to execute register 2 equals x. So the register 2 becomes 1 because the value of x can be copied to register 2, right? So this value going to copy to register 2 and increment the register 2. And then x equals register 2. So that means the value of register 2 copy back to x. So then after this statement, the value of x becomes 2. So you copy it here. And then hopefully, after I finish these 3 instructions, I switch back. And the preprocess 1 going to execute the register 1 equals x, and the register 1 plus plus, and the x equals register 1. However, if things are not actually running as like this, if the computer actually scheduler, remember we use round robin, right? If the computer scheduler says, okay, now I switch to P1, so register 1 equals x, so the value of x is going to be copied to register 1. So value of x, here's x2, copied to register 1. So the register 1 becomes 2, right? And then register 1 increment by itself, it becomes 3. Now, however, after you do this, the scheduler computer actually scheduler going to say, well, I'm going to switch to this here. So after register 1 plus plus, I'm going to execute register 2 equals x. And then register 2 plus plus. Okay. And then register 2 oh, X equals regis 2. I'm going to complete this cycle. So what happens? Now, regis 2 equals X, which means the value of X is going to be copied to regis 2. Okay. Now, what's the value of X at this moment?
Two.
Still 2, right? So regis 2 get value 2. Because register 1 has increment, so the value is 3. But that number 3 hasn't copied back to X yet. So the value of X is still 2. And now I increment the regis 2, so regis 2 becomes 3. And then I actually say regis 2 assigned to X, so the value of X becomes 3, right? And then I switch back. So the next one after this X equals X regis 2, I execute the X equals register 1. Okay. Now, what's the value of register 1? Register 1 copy to X, so it's still 3. Right? Now, do you see the point here? So if you take a look, the overall picture looks like a P has executed X equals X plus 1 twice, right? Here's another X plus 1. And Q also execute X plus equals X plus 1 once, twice. So you have actually total executed 4 times for X equals X plus 1. Now, based on our assumption, based on our common sense, you actually executed X equals X plus 1 4 times. It doesn't matter which one executed it, which process executed it. So you executed this one twice here, and the value of X should be 4, right? Because it's the value of X has been incremented 4 times. Does that make sense? But the reality is the value of X only incremented 3 times. Now, why this happens? Because you actually, the round robin actually switched the CPU back and forth in the middle of these 3 instructions. Okay. Now, these 3 instructions, if we use the critical section, we're going to say these 3 instructions actually should be defined as a critical section. Why? Because these 3 instructions going to be updating the shared variable. So if the instructions that update the shared variable, that should be defined as a critical section. Okay, and these 3 instructions should be defined as a critical section and critical section. Okay. Now, the reason why this thing happens is because it's violate the rule of critical section. Because critical section should be inseparable. Remember the 4 conditions we talked about, the critical section. So if process 1 is in its critical section, the other process cannot enter their critical section. Now this happens, but this rule actually violated here. Can you see the reason? Because when process P is actually running these 3 instructions, and if process P complete the 2 instructions, but this one hasn't started yet, but then it suddenly switched to another process, and another process enter its critical section, right? So here Q also enter its critical section. Now, this is actually kind of scenario that while P is still in its critical section, and the Q start to enter its critical section. So both P and Q are in the critical section. So both the P and the Q are updating the shared variable X. That's the problem. Okay. Do you see the point here? And this kind of situation is called a race condition. Now, when you design an operating system, to support multiple processes, okay, if these multiple processes are sharing the common variable, a shared data. So a process P and a Q both can access this data, both can change the data. You have to make sure while P is in its critical section, that the P is actually changing the shared data. Make sure don't switch away from P, because make sure P just completely finish its critical section before the other process can enter its critical section. You cannot just perform some kind of interleavings. Okay, you cannot have this kind of scenario. Okay, you cannot have an interleavings while one process hasn't finished the critical section yet, the other process just entered the critical section, and both processes are in the critical section. Now they are actually changing the data. So everything just a process, the change of the shared data made by one process is overwritten by the change of the other process. This actually caused the race condition. Okay. Now we know the problem. Now how to resolve that problem? So we use the software solution, right? We just set up the value. So see what's the solution we actually provide. Yeah, we use the solution like use C1 and C2, right? But this software solution is working for two processes. Now, if you have more than two processes, then what's the best approach to this? Okay. Now, the next section is we're going to talk about is the semaphores. Semaphore is a kind of solution to the critical section problem. Okay. Sorry, that's critical section, not computer science. So that's a critical section problem. So the software solution to the critical section problem has several major shortcomings. Number one, the solution works only for two processes. If you use a C1 and C2, and each process set up the process B set up the process 2 set up the C1, process 1 set up C2. So they set up each other's variable. And also the solution is inefficient. And many times it just allows the process to alternate, So it's not working. It's not, at least it's not, very practical. So then we actually, in modern computer systems, they come up with a solution called a semaphores. Now, how this semaphore actually works, okay? A semaphore is, it's just a non-negative integer. So it's an integer, it's a number, okay? So this semaphore is a non-negative integer variable that can be accessed using only two special operations, P and a Q and a V. Okay. Now here's a kind of code I just put in here. V is actually just it's like a function, just to increment the variable. Okay. Now P is basically decrement the variable S. depend on the value of s. If s is greater than 0, then you decrement s by 1. If otherwise, you should wait. So this is the actual implementation using the while loop. Okay. So while s is less than or equal to 0, this condition is true. And then it's stuck in the while loop. Remember, this while loop has an empty body, has no statement inside the while loop. So it's an empty while loop. If the condition is true, it does nothing, but it's stuck in a while loop. You know what? So this while loop is actually check the condition. If it's true, okay, don't move forward. It's just you can think about a while loop like this. Okay, I just use a pointer here. So it's empty body, nothing in there. So there's nothing in there. Okay. So if this condition is true, supposedly for the while loop, it can execute any statement inside, but there's no statement inside. It's an empty while loop. So it's actually just a kind of it's kind of a loop that continue to it's like a spinning in the while loop. Okay. So however, the while loop may be broken if the value of s has been changed. If suddenly the value of s becomes 1, okay? If the value of s is 0 or -1 or any negative number, then this while loop is going to continue to run. But if the value of x is just increased to 1, so then you check the value, the condition, the 1 less than equal to 0, and that condition is no longer true, then you can actually break the while loop and move to the next statement. So the next statement says I can decrement the value of s. Okay. Now the v is just the increment of value s. Okay. Now the implementation of P and Q must guarantee that if several processes simultaneously invoke P or V, the operations will occur sequentially in the same arbitrary order. If more than one process is waiting inside the P for S to become positive, one of the waiting processes is selected arbitrarily to complete the P's operation. Okay. Now, typically, the semaphore is implemented using the hardware. It's not a software code. It's actually like embedded code. Okay. We're going to talk about this a little more because if we are not careful, we're going to fall into another kind of paradox. But at this moment, we just say S is called a semaphore. It's the value that all the process is going to be able to access. Now, how can we resolve a kind of critical section problem using semaphore? Okay. Now, suppose I have a process 1, process 2, process 3, process I, P1, P2, P3, all the way to Pi, and the last process is Pn. So I have n processes. N could be 1. Oh, n could not 1. N could be 3. N could be 4. N could be 5, or n could be 100. You have 100 processes. Now, each process has its own critical section. So these are a fragment of code. Okay. However, with the semaphore implementation, before each process enters its critical section, you have to actually call these function P. Okay. And then once the process complete the process one complete the critical section, it's just called the function v. Same thing with the other process. Okay. Now these critical section might be different code. Okay. Now the only common things that in the critical section, the process going to access the shared variable, whatever the variable is. It is we're talking about. Okay. The shared variable. Okay. So they're all going to access the shared variable. Okay. Now mutex by itself is also a shared variable. Okay. So initially the mutex is set to 1. Remember, mutex is an integer value. It's a number. It's, you know. So if the mutex initially set to 1, now if process 1 wants to enter its critical section, so then it's going to first execute this function p, right? Now, if process 1 is the first process that wants to enter the critical section, so the mutex value is 1, right? So then I call p parenthesis mutex. So the mutex value, 1 will be passed to s. So the s is actually 1. Just compare s equal x 1 less than 0, less than or equal to 0. So the condition is not true, right? So you can actually enter this next step. So you can decrement the value. Decrement the value of s. So s becomes 0. So actually, once they finish, once they pass the actual p, the value of mutex becomes 0, right? Because it decrement the value of mutex. The mutex value is 0. So then when the mutex value is 0, process 1 is in the critical section. Okay. Now, while the process 1 is in its critical section and the process pi wants to enter the critical section, so the process pi is going to execute its own function p. So then process I going to check the p.
We lost you, Dr. Chen.
Yeah, I was just gonna say, I thought my internet cut out or something.
Yeah, because that's happened to me before where like I need to log off and log back on. But since you're talking to me about it as well, I know that that is not the case.
Yeah.
I don't think he's coming back.
Yeah, seems like it.
Well, see you on Thursday.
See ya.